Okay, I want to continue on with the idea that we discussed last time with the game of life, procedural methods, this time returning to Newtonian particles and doing an NBody simulation. And again, I want to do the physics in the GPU. I'll show you, let me get a share screen going here. I'll show you first a Unity simulation here of an NBody problem. And I want you to watch the frame rate here. I'm starting with some 450 particles. Frame rate's around 8. These particles coalesce in that when they collide with each other, they do a little conservation of momentum calculation, and they become a single planet. So as this simulation goes on, we have fewer and fewer particles. Frame rate is abysmal. It's particularly slow, of course, because I'm running Zoom at the same time, but that's the way it goes. As the numbers drop down here, the frame rate hopefully will increase. And I'll remind you that the NBody problem is an order n squared problem, in that when we calculate the force on each particle, there are n of them, we have to go out and measure the distance to every other particle. So for each particle's force calculation, we have to do n calculations of force. And so it's an order n squared. Here the numbers drop down to around 200. We still have an abysmal frame rate. I think at some point here, I'm hoping at some point here, it will speed up as the number of particles drops significantly. This is terrible. All right, it's starting to go up here. We're down to 60 particles, and we're up to a frame rate of 20. Without Zoom, this would be flying, but with Zoom running, this is terrible. Terrible. All right, well, I guess you'll have to take my word for it that that it actually does speed up. It's actually going about 4 times faster than it was when we started off here. So I have one with fewer particles. Let's start this off with 100 particles, see what happens. Let's start it off with 25 particles, see what happens. All right, well, we're not going to get a good frame rate with Zoom running. But the point is, that's a simulation where where all of the physics is done in the CPU rather than the GPU. And what I want to do here is look at doing that calculation in the GPU. And let me just, for a moment here, see if we're going to get any frame rate out of that. So this is, yeah, look at that. This is with 1,000 particles. So 1,000 particles was giving me a frame rate of 1 or 2. This one's giving me frame rates in the 40 to 60 range NBody problem calculating this. It's being done in the GPU instead of the CPU. So what do we have to do in order to do that? By the way, this is adapted from this site, an 8K that flogs my GPU. So what we're going to do here is we're going to use textures to store the intermediate results, the positions, because as with the game of life, we have to have previous states from which we can calculate the next state. With the game of life, we had two textures. I'm going to use a numerical method called Vertex. Vertex is very good at conserving energy in orbital problems. It's the method of choice for doing NBody problems. And the way this works is you take Taylor expansion that gives you your next step. So we have the position, the velocity, the acceleration, this is called the jerk. It's the rate of change of the acceleration, and then higher order terms I don't care about. And I do a backward step. So this is a minus delta t and a plus delta t squared, because delta t being negative squared becomes positive. This one's negative. So if I add these two together, the forward step and the backward step, the delta t cubed terms cancel out. One's plus, one's minus, and the Vn terms cancel out. One's plus, one minus, and I get two of these, and I get two of the. Well, I get one of these since they're over 2 factorial. I can then solve this for the n+1th step in terms of the nth step and the n-1th step and the acceleration calculated at the nth step. This is third order for position. If I were interested in the velocity, I can subtract these two, and I find that the velocity is just the difference between the n+1 and the n-1 step over 2 delta t, and there's no recursion here, so it's not accumulated. The drawback to Vertex is it's not self-starting. It requires 2 steps in order to calculate a third. We need to know the nth step and the n-1 step. We calculate our forces at the nth step, and that lets us step forward to the n+1. An advantage is I don't need to know the velocity, but I can calculate it at any step from the new one and the previous one. I can get it at the current one. So to do this in the GPU, I'm going to need 3 textures to hold these 3 states. One for the nth, one for the n-1th, and I'll use those 2 to generate the acceleration at the nth state, and to project to the position at the n+1 state. One big problem with all NBody problems is how to set up the initial conditions. We have to have positions and velocities. This is going to generate random positions in that kind of spiral circular realm using sines and cosines. And I'm going to make a velocity by displacing the x, y, and z by some small amount, delta phi over r, where delta phi is some small angle. So pix and pix1 contain the initial state and one that's slightly different from it, which will be our sort of setting of initial velocity. I'm going to load these 3 states into the 3 textures. So pix I'll put in texture 0, pix1 I'll put in texture 1, and it doesn't matter what I put in texture 2. I'll put pix in there. Just it doesn't matter because I'm gonna generate a new state for texture 2 in my first step. The access for all of these is through the frame buffer objects that we talked about with the game of life. I have frame buffers with texture, frame buffer 1 with texture 1, and frame buffer 2 with texture 2. And so each of these are going to access the different textures. Texture and texture 1 contain the 2 initial conditions, and texture 2 I'm going to generate. So looking at the Vertex Shader, the Vertex Shader is very simple. We're just going to pass on the GL position from this vector 2 of positions that I'll show you in a second, and a texture coordinate that will also pass on as a variant. A little bit of trickiness that was done in here. Usually with attributes, we've loaded them into a single array. But here, to kind of be fancy and take into account stride, I'm going to load my positions of the 4 corners of my array. -1, -1, -1, -1, 1, -1, and 1, 1. Those are the corners. And here are the S&T texture coordinates, 0, 0, 0, 1, 1, 0, and 1, 1. And I'm loading them into the buffer. But I'm going to assign their positions with a stride. So the stride is 16. These are 32-bit floats. So the stride is 2, and the texture coordinate starts at byte position 8. So we've interleaved these into our data buffer, but we're assigning the positions using this stride to extract their positions. The fragment shader is where we're going to do all the work. Here's some constants that will appear in our calculation. The D is the sampling interval of our texture. E is a softening, and DT is the time step squared. So our 2 samplers, SAMP and SAMP1, are going to correspond to the n-1 and the nth states from which we'll build our n+1 state as we go into our, that will go into our 3rd texture. This is all coordinated with a draw function in the JavaScript, where the 3 textures are cycled through, doing several iterations per rendered frame, the usual thing where we kind of balance our physics step against our frame rate. And there are 3 steps to this. First, with texture 0 in SAMP and texture 1 in SAMP1, and the frame buffer that we're writing to, frame buffer 2, that's going to be the texture 2. And I'm going to draw this little triangle as a triangle strip, this little -1, -1, 1 minus, this little quad with a triangle strip. So that's the first step. The second step, I'm going to now move texture 1 into SAMP and texture 2 into SAMP1, and I'm going to generate to texture 0 with the frame buffer FBO. And again, render, draw the arrays with a triangle strip. The third step completes the cycle. Now with texture 2 in SAMP, texture 0 in SAMP1, and we're going to generate to FBO1, which is texture 1. So schematically, the first step, we use texture 0 and texture 1 to generate texture 2. Then we use texture 1 and texture 2 to generate texture 0. Then we use texture 2 and texture 0 to generate texture 1. And we're back where we started from. In the main, we're going to do the sampling. We zero out the force. We scan through our texture with this offset D and D2 the sampling interval in the X and Y. We, our vector between the points is the sample texture coordinate offset by X and Y, X, Y, Z, minus the R1, which is from the other sampler. And then we calculate our distance squared as the dot product of those, of the vector V. If it's greater than 0, then we're not looking at our self. We add in this little softening that prevents divisions by very small numbers, and I accumulate into my force that vector divided by a times the square root of a. This is a times the square root of a. That's going to give me an r cubed, which is a trick I'll explain later. It's not r squared. So finally, we'll scale up f with a tuning parameter, just some tuning parameter to make things work well, and then do the Vertex update, which is 2 of the R1s, 1 of the Rs, plus the force an times delta t squared, and I'll write that into our fragment color. Remember, that's the frame buffer, not the screen that we're writing it into. So we're storing our coordinates, our vec3 coordinates, in the RG and B channel of my frame buffer. To display this, we also have display shaders. This is going to just sample the texture containing those updated positions with a vec2 of the points that match those texture locations. Here's our projection and model view matrix for rotating the whole business, and we just sample out of the texture at those points, set the point size to 4, and set the color to be white. I think I did some fancier things with the color in the one that I displayed. In the JavaScript, we have our vertices that we want to match that texture. So these are going to be kind of a checkerboard of particles across my range from d over 2 to d, d over 2 to d, and I'm pushing them in there, sending the points location as vertices to the program. The draw scene function, so this is what's going to actually draw it, is going to use the show programs, the programs that are for displaying, all the projection and model view stuff, clearing the screen and the depth buffer. I'm going to use blending here with a GL source alpha, and I'll display those points that are being moved around by the other shader. The fragment shader for display just catches the color and assigns it to the fragment color. So that's pretty complicated, but it works very well. So here I'll run this. Remember, this is 1,000 particles, and with just 400 particles doing it in the CPU in Unity, we got frame rates of 2. Here we're getting a frame rate of 50. I can rotate and maneuver this thing, zoom in and out. Whoops, don't zoom too far. But I've formed these little clusters. If you watch this long enough, the clusters kind of merge with each other and do all kinds of interesting things. N-body problems are hard to get stable configurations where things stay together. Getting the initial conditions right so that the cluster stays together is always hard. These things are constantly sort of flinging particles out into the world. And I'll post this and let you play with it at your leisure. So let me stop sharing here. And that ends the lecture. I'm going to stop now. I'll see you all in class. Bye.